The final speaker this afternoon is Kim Anderson, also from North Carolina State University. She's now an instructor in Textile Technology Management department, and she's pursuing her PhD degree while teaching. Her interest is in medical textiles and conductive textiles, etc. This afternoon, she will talk about what's the topic? Yeah, the road to wearable electronics.
Take about 5 minutes. This is a very, very exciting field. I think it has tremendous potential for the textile industry. There's just so many different applications that a flexible, lightweight, conductive textile could be used. Ironically, conductive textiles have been around for many years, and they have been used in a variety of applications. However, the electronics industry in the last 15 years has undergone some major developments. Electronic components now are smaller, literally on the micro and nano level. They're also much more powerful. So by incorporating these electronic components in a conductive textile, we could possibly design much more sophisticated products. This new genre of products could actually be interactive, multifunctional. They could be designed to respond to certain environmental stimuli, such as pressure or temperature or moisture. The first thing we have to do, though, to design these products is we have to produce a textile that has appropriate conductivity. And that's what I'm going to concentrate on today, are the different methods of imparting conductive properties to a textile. There is a plethora of different processes, so I'm going to concentrate on those that have the most potential and the ones that are most widely accepted in the textile industry. I'll start with fiber processing, and then you can also impart conductive properties with yarn formation or after the fabric is formed. You can impart conductive properties during fiber processing with metallic salts, galvanic coating, and vacuum spray. Now, these three methods, I'm not going to go into any detail because they have some limitations. Metallic salts, you get low conductivity, so it's really just for static dissipation in carpet. Galvanic coating is very complex, it's expensive, you can only do it on a conductive substratum, so therefore it's limited to carbon and graphite. Vacuum spray, you can also do this on fiber as well, on fabric as well as fiber, but you get low adhesion between the metallic coating and the fiber or fabric. So I'll detail draw blending and then go into metallic particles. Let's just skip that. The draw blending is done on a short staple system. You have a sliver composed of some metal alloy and then another sliver composed of conventional textile fiber, and you bring them together at the drawing process. You can do this with little modification to the spinning frame. You get fairly high conductivities depending on which metal alloy you use and depending on the blend level. And the yarns do have lower tenacity, but that doesn't negate their applications in a wide variety of products. There are some disadvantages. They're expensive, but anytime you use a metal fiber in any of these processes, you're going to have some expense. So that's not really specific to the process. A homogeneous blend can be difficult because the metal fiber is 5 times heavier than conventional textile fiber. And then metal fibers are brittle, so they can abrade your equipment, your spinning equipment. And they have a metallized hand. Again, this isn't specific to this particular process. Any of these processes where you're putting a metallic coating or using fibers that have a metallic coating, you can possibly get certainly a metallized hand. coating fibers with conductive particles. This is one of the oldest ways of producing a conductive fiber. It was first done with a carbon that was dispersed in a resin. Today, or more recently, they've been using a high concentration of a silver and dispersing it with a resin and then coating the fiber. You can get high conductivities. There's a patent out now which they've designed a fiber. It's polypropylene, and you don't have to use the resin because they've engineered the fiber so it has longitudinal cavities which entrap the particles. Therefore, you don't need the resin to adhere the particles to the fiber. Imparting conductive properties during yarn formation. There's a number of different ways. I'll start with coarse spun yarns. Coarse spun yarn has two components. It has a core and a sheath. This can be done on most spinning frames. You introduce a roving, or take the roving through the first two drafting systems, and the roving is going to become the sheath of the core yarn. Then you introduce the core component at the nip of the third roller, and that roving just surrounds that core. And to produce a conductive yarn, you could use like a flexible metal for the core, or you could use another type of a roving that's been treated with a metal or conductive material. A wrapped yarn also contains two components. You have a wrapper, which can be mono or multi-filament. You have a core, which can be twisted or twistless. You can wrap the yarn in the S or the Z direction, and you can vary the number of wraps per inch. You can also wrap the yarn in an X configuration. There's a patent out now where there is a conductive yarn using the X configuration where they use metal filaments, and the yarn is reported to have a good flex, as well as doesn't lose its conductivity in various stress-strain conditions. Bi-component yarns, there's two different components, and this can be wet, dry, or melt spun. There's two types of configurations. There's side-by-side and sheath core. This is how the side-by-side and sheath core are formed. The polymers are brought together at the point of extrusion, right here. And the side-by-side has two chambers with the or two chambers with the two polymers, and of course the core sheath has a core with this chamber right here forms the core, and then there's two sides to form the outside or the sheath of the yarn. You can change, or you can get different configurations. The first two show different side-by-sides, and then the next two show different sheath core configurations. You can also change the shape of the orifice to get different bi-component different shapes. Going back, sorry. Well, bi-component yarns, the patent literature is replete with conductive bi-component yarns, and I think that has tremendous potential. They've put fine carbon powders in the sheath and the core. They've also used metal oxides in the core and the sheath, or both. Braided constructions, of course, this is one of the oldest ways of creating fabric. It's a diagonal interlacing of yarns. The two-dimensional construction, you can get small, flexible fabrics that could basically be used as yarns. And you could put in one or two of the positions a conductive yarn to get a braided construction that was conductive. Composite yarns, we have single yarns that can be brought together and plied, and then the plied yarns can be brought together and cord. At any point, you could have one of these components be a conductive material to produce a conductive composite yarn. And there's just all different types of composite yarns, and I'm just going to quickly go over these. GIMP, which can have a twistless core or a twisted, and then you can surround it. You can bring the case cord and the GIMP together to do upholstery cord. And of course, upholstery cord is a decorative edging for upholstery, but this could be used as a conductive yarn depending on your the end use and the properties you're trying to achieve. Novelty yarns we typically see novelty yarns in high-end upholstery and apparel fabrics, but anytime you have two components, you could introduce one of those components as either a flexible yarn or a yarn that's been treated with a conductive material. Imparting conductive properties after fabric formation, I'll start with electroplating. Plating. That's the continuous deposition of a metal and an aqueous solution onto a substratum. Basically, the metal coating is formed from a chemical reaction that's taking place with a reducing agent and a metal ion. There's no electricity involved in this process. It has a lot of advantages. You can coat almost any substratum. You can use a variety of metals. You can also use two different metals simultaneously and coat the fabric. You get uniform thickness. The deposition is fairly simple, but the process is not. There's literally volumes written about this particular process. And the coatings can have unique mechanical and magnetic and chemical properties. The disadvantages is it's expensive and it's less intensive. Since you're dependent on the reduction of that metal ion, it's not as intensive as some of the other processes. The sputter process, this actually is a very old process. I think it was discovered in the mid-1800s, and they first started cutting mirrors, and then in the early 1900s they started cutting fabrics. But you can get very high conductivities with this particular process. You can cut a wide variety of substratums, and you can use almost any metal. It takes place in a vacuum chamber. You have a target material, which acts as a cathode, and then you have the substratum or the fabric, which acts as an anode, and you apply electrical potential, and that produces a glow discharge. Glow discharge is basically a positive ions, free electrons, and neutral particles. The target, reduction's taking place, so it's gaining electrons. Therefore, those positive ions accelerate towards that target. And in response, the target shoots out at a high velocity these atoms, which coat the fabric, very thin coating and very, very uniform. It has many advantages. It's, as I said at the beginning, you can coat almost any type of material. There's excellent adhesion between the coating and the substratum. Very uniform thickness and distribution, and you can achieve very high conductivities depending on what metal you use. The disadvantage is it's expensive, and it's expensive because it's slow. It's like 20 to 100 feet per minute, so it's a very slow process. Evaporative deposition also takes place in a chamber. When you have your fabric, let's take some choreographing to talk to the microphone and use your pointer at the same time. Your fabric's rolled up, and the metal here is heated up to a temperature that maximizes evaporation. And as the fabric comes in contact with that metal, it evaporates onto the surface, forming a coating, a metallic coating. The advantages, you can use different types of metals. The thickness of the coating can be varied. You can literally get like a millionth of an inch to thicker coatings, and it's higher speeds than the sputter. And it's used in a wide variety of products. Coating fabric with utilizing conventional techniques. The direct coating has been used to coat aluminum onto fabric. You have the knife, which actually is coating the material onto the fabric. You can vary the thickness by varying the distance of the knife to the fabric. You can also coat more than once. You can coat both sides of the fabric. You get good abrasion and chemical resistance. There's superior adhesion between the coating and fabric, and good flex depending on what carrier you use. Coating fabrics with conductive polymers. In the late 70s, it was discovered that certain polymers could be doped, and doped is basically they could be oxidized or reduced, and they would become very highly conductive. Unfortunately, it also changed their thermal stability and their solubility, so it made them very hard to process using conventional textile methods. So in the 80s, they started thinking, why not use a yarn or fabric as the integrity and the strength, and just use the polymer to impart a conductive property. So there's a lot of experimentation going on in this particular field. They found that polyaniline and polypyrrole are the polymers of choice. You get excellent adhesion between coating and textile, non-corrosive properties. There are some disadvantages. Sometimes they're not, the solvents aren't soluble with the other textile chemicals. They're also not compatible. And there's some environmental regulations, basically restrictions to the solvents that are used in this particular process. But this is a very active field of research. In conclusion, as I said at the beginning, I think this is just such an exciting field. Merging the two fields of electrical engineering and textile science and technology and design, some possibilities of designing very sophisticated fabrics that could interact with the environment. And really the applications are for many diverse fields in medicine as well as recreational, military, etc. So it really is, I really think there's a lot of potential. Thank you.
Any questions? No questions?
Yes. I was questioning.
Question? Yeah.
It's a very good review of the field and the technology available. Would you please elaborate how much you have done in the North Carolina University in your laboratory? What techniques have you?
What I've done specifically, my research?
Yes, correct.
Okay, my research has been on the pressure, textiles that respond to pressure, and some of the most obvious end uses for that would be carpet. You can tell when someone comes in the room and the weight, but it's amazing. If you get a few electrical engineers and textile people together, just all the different products they can think of. And the pressure-sensitive textiles are also being used for crash dummies. You know, when automobile makers are doing testing, they have to assess the damage to the driver. And so if you cover that dummy with like a pressure-sensitive textile, you could assess exactly where the impact was and the extent of the impact. And there's just so many different things you could do with just a pressure-sensitive textile. Did that answer your question?
Yes, for the pressure-sensitive textiles certainly is very interesting. What method have you used? And have you have any calibration and sort of curves which you can really detect accurately the pressure levels? Do you have
levels?
Yeah. Do you have any data to show us?
No, I don't with me. Dr. Seyam, the electrical engineering people might, because they have done a lot of testing. We, of course, weave the fabrics and then we give them to them and they collect the data. So I'm not, I could get you some if you would.
Okay, thank you very much. Thank you.
I have a question.
Okay.
What's the reliability of these products?
Reliability, washability.
Washability and wear life, etc.
Well, the washability, I would imagine, would be a PhD project. And I really can't answer that question.
And somebody buys this for $5,000 and then it goes wrong after 2 days. I mean, what do you do?
Don't wash it.
I mean, conductivity is okay, but you know, suppose you're getting some signals or getting some sort of electronic communication done, and there is lots of room for failure. So it's like a digital printing. If one of the nozzles go wrong, the entire fabric is ruined. One time, when I was working for industry, we tried to do this, and then we could not produce more than 5 yards of fabric. So I just wonder if you are not faced with the same sort of dilemma.
Oh, certainly. In some of these products, you're really are life-saving products. I mean, you know, especially in some of the applications. So, if something you have to have a low failure rate. Certainly, we're striving for the 6 sigma. I would imagine in some of these products.
Probably 10 sigma.
Can I answer you the washability? Washability is really not a problem at all. If you can put the devices and electronics inside fiber, you will not really deal with the devices and electronics on the surface at all. Everything is inside. You can also laminate the structures if you want, depending on the end use. And don't think about this. This is not everything. There are carpets, wall coverings. Imagine that you can have a system that once you enter from your door, your computer is on, your temperature is adjusted for you, it recognizes you, security systems, child security. If the child is wet, it can let you know. There are many advantages or many applications that people are dreaming of, and they are coming, and they become real very soon.
Let me just give you an interesting hindsight of all this. I was in Seoul 3 years ago, and one of the housewives worried about where their husbands are, told me that they have a technology to pinpoint where and which street her husband is.
Well, this
And the government decided to ban that for the time being. So that's okay. Any other?
Find the child, yes. Find the husband, yes.
Any other questions? If not, let's applaud all. Oh, you have one. Okay, I'm sorry. Could not see you. Right.
Just please, you mentioned that it has a problem with the environment. How can this affect the human being bodies? Because if it's, if it has environmental problems, then
The question is, does it not affect the human
Yeah.
rather than environment?
Yeah.
Well, the environmental restrictions I was speaking of was specifically with the conductive polymers on the polypurol and polyaniline that to process them and make them into a coating to coat as fabric. So I wasn't really specifically speaking of the conductive product in itself. I was talking specifically of the conductive polymers and how you take them to a polymer to a coating.
I suppose what she means is you're wearing electricity.
Yeah.
So would that be?
Can you answer that, Dr. Seyam?
Environmental problems are going to be there, and we need to solve them. But talking to our electronics electrical engineers and computer engineers, they said this is going to be very low power. You may drive these from solar energy. You may drive it from your body heat. So I think this is not going to be a problem as far as affecting a human. And like I said, you may find the electronic textile for a human very limited, and it has a specific purpose. It's not going to be probably big. It may be big in other things. Again, think about all these fabrics you see around you. Wall coverings, carpeting, cars, everything got fabric. Can't see you.
might have a problem environmentally then.
I agree with you. We have to resolve this issue later on. This is this is just right.
Okay, that's fine. Thank you. Okay, thank you so much. Thank you.
So, I think we will be solved. Right now, the new area of research, interest interest, all the civilians are.
Thanks.
All right, I think in view of the time, we should stop here. Let's applaud all 4 speakers.